This question is a little bit involved, but something that we can definitely do. So it says a large cannon is fired from ground level over a level ground at an angle of 30 degrees above the horizontal. Muzzle speed is 980 meters per second. We neglect air resistance. We want to know how far the projectile will travel in a horizontal distance before striking the ground. So this is a little bit of a confusing problem, but it just says that we have a cannon that has some muzzle velocity, V0. It's at a 30-degree angle, and the projectile is going to go up and eventually down. And we want to know how far is that distance d. Well, I start this problem, I've drawn a picture. I'm going to set this point right here as my 0, 0 point, positive x, positive y being in a normal way. So up is positive y, horizontal to the right is positive x. So now I'm going to go through and list my initial conditions and see what I know, what I don't know. And hopefully it'll give me an idea of where I want to begin this problem. So I know that my initial position is 0, 0. My cannon fires at 0, 0. My initial velocity in the x direction, my initial velocity in the y direction are going to be given by, are going to be related to some initial velocity that we're given. The initial muzzle velocity we knew was V0, and we want to know what are the x V0 y and the V0 x. We want to know the x and the y components of this. So I'm using this little triangle, and I see that V0, that angle theta in there, I'm going to be dealing with V0 x is going to be V0 cosine of theta, and V0 y is equal to V0 sine of theta. Opposite over hypotenuse gives me my sine from SOHCAHTOA, and the middle part of SOHCAHTOA, the adjacent over the hypotenuse gives me my cosine. So I'm checking my angles. I'm never believing what angle I'm given is the right one. It just makes sure that I don't screw up angles later on. All right, my acceleration in the x direction, well, this problem is in free fall. So in the x direction, there is no horizontal acceleration, and in the y direction, there's minus g. Our acceleration points in the downward direction and has a value of minus g. And I know something about my final velocity, or final positions. My final y and my final x. Well, my final y is actually kind of easy. I go up and I go back down. I end up at the same spot I began with. My final x, on the other hand, is how far do I want to go? This is actually the value that I'm solving for. So I look at these equations, or these values, and I see that I have initial positions, I have initial velocities, I have accelerations, I have final positions. I don't know one of them. I'm missing time. Time would be a nice value to have, but I have two full sets of data. This makes me really, really want to use, especially since I want to solve for d. It makes me want to use the equations, the general equations, x is equal to x naught plus v naught t plus 1/2 a t squared. So I'm going to look at the x component first. And the x component, x is equal to, or our final x is equal to our initial x plus our initial velocity in the x direction times time plus 1/2 ax t squared. Now I'm going to go through and substitute some stuff in. I know that this value is d because that's what I declared it to be. I start at position 0 in the horizontal direction. I have an initial velocity v0 cosine of theta times time. And last but not least, I have an acceleration of 0. So d is equal to v0 cosine of theta times time. If I know time, I have v0, I have cosine of theta, I can get d. Unfortunately, I don't know the value of t. So in a lot of these problems, we use the up and down direction, the vertical direction, to solve for our time. It takes a certain amount of time to go up and back down. The timer stops when we hit the ground, so it's more of a vertical component. So final y is equal to our initial y plus v naught y of t plus 1/2 a in the y direction t squared. My final position in the horizontal or in the vertical direction is 0. My initial is 0. Substituting in for v naught y over here is v naught sine of theta, quantity times t, plus 1/2 minus g t squared. So I substituted in my value for negative g, gravity in the downward direction where up is positive. All right, I'm going to grab another sheet of paper because I'm quickly running out of room. So hopefully we can still get these equations. Equations we had from before is we had our horizontal and our vertical equation. So I'm going to continue with the vertical direction because I'm not quite finished there. So still in the y direction, I get that y in the y hat direction, I get 0 is equal to v naught sine of theta times time minus 1/2 gt squared. So this is 0 is equal to v naught sine of theta minus 1/2 gt quantity times t. So I just pulled out a factor of t from there and a factor of t from there. So this says that my t can be 0 or my t can be equal to, let's see what this is, going to be 2 v naught sine of theta over g. So either this term has to be 0 or this term has to be 0. Well, when time is equal to 0, we started at our 0 position. So that one's kind of the boring answer. We knew that one already. Mathematically, it works, which is good. But in terms of where it lands, we actually want the second one. So the one that we're going to be using is this second equation. So write down the x component one again. That was d is equal to v naught cosine of theta times t. So at this point, I'm going to combine these two equations. Don't need this anymore. I'm going to combine these two equations together. So I'm going to just say d is equal to v naught cosine of theta. That was my original stuff. Now my time. Well, time is 2 v naught sine of theta over g. Or d is equal to v naught squared over g times 2 cosine of theta sine of theta. And if we really want to be fancy, 2 v naught squared over g times the sine of 2 theta. This is a double angle formula. 2 cosine of theta sine theta is equal to sine of 2 theta. So at the end, I go through and I'm going to plug in my values. I have v naught was 980 meters per second squared. G was a value of approximately 10 meters per second squared. And my sine of 2 theta, that's the sine of 60 degrees. And the sine of 60 degrees is going to be, let's see, you got to remember, if I have 60 degrees here, I know that there's 1, 2, and square root of 3. So my sine of 60 degrees is equal to square root of 3 over 2. So this is, about 1,000 squared over 10. And this is units of meters squared, meters, seconds squared, and seconds squared. I get units of meters, and then square root of 3 over 2. So I have this to be 10 to the 5th divided by 2 times the square root of 3. So I am looking back at my answers. Square root of 3 is above 1, below 2. So it doesn't quite cancel with this, but I'm looking on something that's on the order of 100 kilometers, a little bit lower than 100 kilometers. So 170 is too large. These are too small. So I'm left with answer choice D is the correct answer. So this works out to be 85 kilometers. So all we did was solve our horizontal position versus time, figured out that we needed time. We solved our vertical position to give us time and then substituted back in. There was a fancy little sine function in here, but everything works out pretty easy. This equation that we got right at the end over here is our range formula. So if you remembered that formula, something that I don't always remember. I know it exists, but I don't always necessarily remember that it only, or I remember that it only works for horizontal, so a lot of times it's not useful for me, but you could use it.